Hello everyone, this is Emmanuel from Cornell, and here I give you a re-recording of my recent VLDB 2018 talk on vocalizing large time series efficiently, which is joint work with two amazing students, Mark Bryan and Ramya Narasimha. Alexa, how did the stock market vary over the day? Now that's an example where as an answer you expect a concise voice description of a time series. Typically, when analyzing a time series, we assume that results are presented to users via visual interfaces such as screens. Here in this paper, we address a complementary scenario, assuming that query results are generally communicated via voice output. And that is motivated, first of all, by devices and services like Google Home, Amazon Echo, Microsoft Cortana, Apple Siri, which are primarily designed for voice-based interaction, so often they don't even have a screen. And on the other side, we are thinking about visually impaired users who generally cannot benefit from visual output and for whom voice-based interaction might be an attractive alternative. Of course, voice output is very different from visual output. For instance, with visual output, all information appears at once on your screen and it stays on your screen. So users have a lot of time to study different parts of a time series on the screen repeatedly at their own pace. Things change for voice output because voice output means that information is revealed gradually and it is fleeting, meaning that you have access to each piece of information only during a very short amount of time, and you cannot do it at your own pace, but it's the system that chooses the pace for you. So typically you want to commit everything you hear to your short-term memory in order to be able to work with it efficiently. And all of that makes it quite challenging to communicate information to users via voice output. So the first question that we are addressing in this paper is how we can effectively communicate high-level information about a time series to users via voice output without overwhelming them. And then the second question that we address is how can we generate those answers efficiently? And here efficiency does not only relate to the efficiency of speech planning, but also to efficiency of query processing, because we assume that the time series to vocalize is generated on the fly as a result of a query. So let's first of all think about our speech structure and about our problem model. So first of all, it is quite hopeless to talk to users about single data points in a time series. Here, for instance, you see an extract from a user study that we performed, stating essentially that typical users cannot remember much more than 3 to 4 data points of a time series after listening to a voice output, and also that is only possible if the numbers that appear in this voice description are very simple. It's rounded numbers. So, and because talking about single data points is kind of hopeless, we rather switch to a higher level of abstraction and generally describe a time series as a sequence of patterns. And here we assume that a library of pattern templates has been provided for us. So each pattern essentially corresponds to a function, and for the moment we support piecewise linear functions together with an associated verbal description of that function. And this verbal description contains placeholders for times and for values, which allows us to scale those patterns to different time and value ranges. Using such patterns, we can, for instance, describe the financial time series that you see here by chaining two simple patterns. As you see here, we could say to users, from April to August, the price rises from $2 to $6. Until October, the price falls to $3. And this, of course, only approximates the true data. I mean, literally, the verbal description corresponds to the development that you see in the plot in green. It doesn't perfectly approximate the data, but it comes somewhat close, and we can calculate the error of this approximation by calculating, for instance, the mean squared error between the actual data and the approximated development. Now, approximation error is one metric that we care about, but there are others. For instance, the length of the generated speech, which relates to speaking time, and also the complexity of the speech, meaning the number of values that users need to remember. That is one example describing the time series. I'm going to give you a second example here, which, as you see, approximates the original data more closely, but on the other side, it's longer and a little bit more complex. Now that we have seen the speech structure and the metrics that come into play, we can give a formal problem statement. We assume that we are given initially a query whose result is a time series that we want to describe to users via voice output. And the second input is a library of speech patterns that we use in order to construct the speech describing the query result. Now, our goal is to find the speech minimizing approximation error among all speeches that respect the constraints on speech length and speech complexity. How can we actually find such speeches? A first possibility, a naive approach, would be to perform two separate steps. In the first step, we generate the entire query result. In the second step, we find the speech that matches this query result as closely as possible. And first of all, this requires that we have a function which finds the speech that optimally approximates a time series. And while I'm not going to go into detail here, you can find a corresponding method in the paper which generates guaranteed near optimal speech approximations under given constraints via a dynamic programming approach. Now, I called this approach naive because there's a mismatch. We are generating potentially a very large result. It might be expensive to generate that result, but we can only transmit a very coarse-grained high-level description to users via voice output. So a lot of those details of the result will in each case be lost. And intuitively, it seems to make sense to generate, instead of the entire query result, just a couple of result samples. And then we can hope that based on those samples, we can still generate an optimal speech description. So here we assume that we can generate parts of the query result at specific time points. And in the paper, we describe a class of queries for which that is actually possible. So the only decision that we still have to make here is picking those time points at which we generate result samples. And of course, we could simply select those time points with uniform random distribution. But as we will see in the experimental results later, doing that actually leads to speeches of a relatively bad quality. So instead of doing that, we propose a more sophisticated method to select those time points for result sampling. We propose to formalize this as an instance of optimal experimental design. And the goal in optimal experimental design is generally to optimize experimental setup in order to gain the maximum amount of information by performing those experiments. And in our specific scenario, an experiment essentially corresponds to taking query result samples at specific time points. So the tuning parameters are the time points at which those samples are taken. And the goal of our experiments is to gain enough information in order to narrow down our choices between different coarse-grained speech descriptions. So in the paper, we propose a specialized method for our scenario, which implements this high-level principle. It's an iterative algorithm which performs the following steps in each iteration. So first of all, we generate random samples from the input query result, and we commit them to a result cache. Then we take several bootstrap samples from that result cache in each iteration, and for each of those bootstrap samples, we generate an optimal speech description. Now, those speech descriptions have been generated for different result samples, so it will be slightly different. And we compared those speech candidates in order to identify time points at which they make widely different predictions, which makes those time points particularly interesting for taking more samples in order to narrow down our choices. But of course, we cannot take samples at all interesting time points because there is too many of them. So we formalize the problem of selecting optimal time points for probing as an optimization problem, and we propose an algorithm that selects a guaranteed near optimal batch of sampling points with a fixed cardinality. And those sampling points from the input to the result sampler, which in the next iteration will generate result samples at exactly those time points. And this continues for multiple iterations until a timeout is reached. In the context of interactive data analysis, you might want to set a timeout of around 500 milliseconds or less, for instance. And once the timeout is reached, then we pick the speech which currently seems most promising, and we start speaking it out to the user. Now, we compared those different approaches that I have just mentioned: full query execution, uniform sampling, and sampling based on experimental design. Here, for instance, you see results for query execution time on simple range queries on a 2.5 gigabytes dataset containing Bitcoin prices. And as you see here, the execution time for full query evaluation is often prohibitive in this context for interactive analysis, while sampling decreases execution times by orders of magnitude, and while experimental design takes a little bit longer than uniform sampling because we spend more time figuring out what should be the time points at which we sample, we see that execution times for both of them are still somewhat comparable. And here we see the quality of the generated speeches. And here, of course, full query evaluation leads to speeches with minimal approximation error, while on the other side, speeches generated via experimental design come quite close to optimal quality. And that is not the case for uniform sampling. As you see, we sometimes have high errors. So those results indicate that experimental design offers an attractive trade-off between execution time and result precision. And this is only an extract from our experimental evaluation. You find more experiments in the paper on different data sets with different query types, but they show similar tendencies. Now here we're comparing different vocalization methods, but time series vocalization is an unusual method so far. So we also wanted to compare to other high-level types of interfaces. So first of all, we compare against the traditional visual interfaces, and then we also compare against sonification methods, which have been proposed in the context of assistive technologies. And here we essentially transmit a time series by translating it into a melody pretty much, where pitch correlates with y-axis value. In order to compare those interfaces, we performed a user study. We recruited 20 crowd workers for each of those interfaces, and we gave them an interactive data analysis task where we can measure their performance. So we asked them to analyze a financial time series and to propose buying and selling dates, and in order to maximize their virtual gain. And then we can measure their performance by the amount of money that they would have made based on those buy and sell decisions. And we also incentivize those crowd workers and promise them a real-world monetary reward based on their virtual gains. First of all, you see results for visual interfaces compared to audio interfaces. And our goal from the start was not to beat visual interfaces because we focus on situations where visual interfaces are not available, but we wanted to see whether the performance of users with vocal interfaces at least comes somewhat close to visual interfaces. And as you see from those numbers, that is definitely the case. So the quality of user answers degrades by about 16% only when switching from visual to audio interfaces. So there is some degradation, but still results are somewhat comparable. So it seems that we are able to transmit the most important tendencies in the data via voice output, at least for simple data analysis tasks. For the users of audio interfaces, we gave them the choice for each query to select between vocal output and sonification. And in order to compare those two audio interfaces, first of all, we analyzed the logs on our server in order to find out whether users tend to use vocalization or sonification more frequently. And here we get a clear picture. Users use vocalization more frequently. And also when asking them directly about their preferences between the two, it turns out that 3/4 of users express some or a strong preference for vocalization, but only a small percentage prefers sonification. So, as conclusion, there's cases where you want to complement visual output by vocal output, because visual output might not always be available. We have proposed a combined processing and a vocalization strategy which transmits the result of time series queries via voice output to users. We've shown that it is possible to perform simple data analysis via voice-based interfaces, and we have compared to visual interfaces. And also we have shown that users prefer speech output over non-speech output. Thank you very much for your attention, and don't hesitate to write me if you have questions.